This is section 10.6, all about gas mixtures. And I'm going to show you here, to give you a little example of a gas mixture that we could have. Let's say we have a container. We'll draw a little container here. And let's say this is a rigid container, so it's not flexible. It's got a lid on it too. And we're able to put gas in and out of this container. Now, up until now, we've just talked about gases, individual gases, and how they behave with respect to pressure, volume, number of moles, and temperature. We're going to talk about pressures now. So let's say if we somehow are able to place into this this container with a lid on it 10 moles of oxygen gas, and you know those little diatomic oxygen molecules, they would be bouncing off the surface, bouncing off each other, and creating pressure inside of this this container. And we could calculate the pressure very easily if we knew, let's say the pressure of the oxygen, if we knew how many moles, which we do, which 10, and the ideal gas law constant, and we knew the temperature, and we could divide this by the volume of this container. We could easily calculate, using the ideal gas law, the pressure that's in here. Well, what if we also put in here some other gases? Let's say we put in 10 moles of nitrogen gas. And also these little diatomic molecules would be bouncing off things as well. And so we could also calculate the partial pressure, what we call partial pressure of the nitrogen, and we would do it the same way, dividing the number of moles by volume after multiplying it by ideal gas law constant and temperature. What we're saying is these pressures, these individual pressures for individual molecules are what we call partial pressure. And so let's kind of scroll down here and take a look at this a little bit more. So first off, we'll just define partial pressure, as we said, is the pressure exerted by a single gas in a mixture of gases. So the air that we're breathing right now as we watch this video is a mixture of gases. We've got carbon dioxide and oxygen and nitrogen and some other trace elements in there, and compounds. That's a mixture of gases. We have Dalton's law of partial pressures, which is a useful law, and what it says here is the total pressure is equal to the sum of the partial pressures. Partial pressure 1 might be the pressure of, let's say in the above example, was the oxygen, and we could add that to the pressure of, let's say, the nitrogen, and so on and so forth, and that would be equal to the total pressure within the container. Okay, let's look now at an example where we're asked to do a little bit more here, and it says 10 grams of oxygen and 10 grams of nitrogen are placed in a 5-liter vessel at 50 degrees Celsius, and we're going to be calculating the partial pressure of each gas and the total pressure in the container. So the first thing we're going to do, let's start with our oxygen here, and we're going to use, to calculate pressure, we're going to use the ideal gas law, PV equals nRT, and we need to figure out the number of moles to start off with. So let's take our 10 grams of oxygen, and we're going to convert that to moles of oxygen by dividing by the molar mass of oxygen, and that gives me 0.313 moles of O2. Now I have N, and all I have to do is solve this guy for pressure, so it's going to be pressure is equal to the number of moles, 0.313 moles, multiplied by the ideal gas law constant, 0.0821 liters atmosphere moles Kelvin, multiplied by the temperature. The temperature was up here, was 50 degrees Celsius. Convert that to Kelvin. We always convert to Kelvin. 323 Kelvin. We're going to multiply that, and we're going to divide everybody by the volume, and the volume of this container was 5 liters. And I'm going to double check. I've got moles canceling, I've got Kelvin canceling, I've got liters canceling, and I'm left with an answer in atmosphere. And so I get the partial pressure of the oxygen in this container being equal to 1.66 atm. If you'd like, you could pause the video right now and see if you can do the calculation for the partial pressure of the nitrogen, or you can just wait, and I'm going to do it anyway. So if you want to pause it and do it now, go ahead. Okay, now I'm going to calculate PV equals nRT, and this one is going to be for the nitrogen. We have 10 grams of N2. We're going to divide by 28.02, which is the molar mass of nitrogen, 1 mole of N2. And I'm coming up with 0.357 moles moles of N2. Basically, I'm going to plug this into the equation above. Instead, I'm going to substitute it in right here and just use the same equation. Everything else stays the same. Run it all the way through. And I get an answer equal to, once I do that, of 1.89 atm. So there's my partial pressure of my nitrogen. Now, right over here, I'm going to do my total pressure is I just have to add the two together. So it's going to be 1.89 for the nitrogen plus 1.66 for the oxygen, and that comes out to 3.55 atm as my my total pressure within the container. Okay, we scroll down here. We're talking about a slightly different topic, but very useful, and that's the idea of mole fractions. Now, what a mole fraction is going to be a ratio of number of moles to total moles. Essentially, all this is the percentage without multiplying by 100. And we're giving you an example. If we had, let's say, 90%, without multiplying by 100, that would be 0.90. That would be, if we were dealing with moles, that would be 0.9 over 100, or 0.9 over 1, essentially. So there's a formula that is given to you on your equation sheet for a mole fraction, and mole fraction is denoted by X. And we say that X is moles of 1, whoever we're talking about, over moles total. And that's our formula. Okay, so that's the mole fraction for X. Now, there's also a very important formula that we use for gases, and that is we can calculate the partial pressure of a gas, partial pressure of whoever this is, by multiplying the mole fraction of that gas by the total pressure. And so once again, we get that mole fraction from this formula here, which is just essentially the moles of one gas over the total number of moles. And so let's do an example of this here, and I see a typo already. I'm going to fix that right on the spot. There we go. And it says at 1 atmosphere, 78% of air molecules are nitrogen gas. What's the partial pressure of nitrogen gas? And so this is going to be really easy. We're just going to take 0.78. Essentially, I'm just dividing by 100. And then I'm going to multiply that by 1 atmosphere. And so obviously 0.78 atm. So that we would say that would be the partial pressure of the nitrogen gas. Real super easy question, but let's look at the next one that gives us a little bit more in-depth question, although not much more challenging.
Margarita, Ariel.
Okay, so they're giving us a problem with a mixture of gases. We have 3 different gases. We have 1.5% carbon dioxide, 18% oxygen, and 80.5% argon. And we're being asked to calculate the pressure of the oxygen if the total pressure of the gas mixture is 745 torr. So we're going to say, okay, 0.18 is our percentage, our mole fraction of the oxygen. And we're going to just multiply that by 745 torr. And so this is going to give us 134 torr for our pressure for just the oxygen. Now, they're going to ask us another question. If the vessel is 120 liters at 295 Kelvin, how many moles of oxygen are present? Whenever we see moles in a gas law problem, it really tips us off that we're going to use the ideal gas law. And so I'm going to use the ideal gas law in this problem. And so moles of oxygen present. So what I'm going to do is just solve this for moles. Moles are going to be equal to pressure times volume divided by ideal gas law constant divided by, or multiplied by temperature. And so I'm just going to plug some values in here. We said up here already that the pressure was 134 torr. Now, almost made a mistake here, and I almost forgot to convert to ATM because we're using ideal gas law constant. And so I'm going to go ahead and do that. Then I'm going to multiply that by volume, which in this case our volume is 120 liters. We're going to divide all of this by 0.0821 liters ATM moles Kelvin. And we're going to multiply that by temperature, which was given as 295 K. And Kelvin cancels, liters cancels, tor cancels, ATM cancels. We're left with moles, and that's what we're looking for. So we run this through, and we get 0.872 moles of oxygen needed to work in this reaction, or I'm sorry, not this reaction, in this gas mixture. We're going to go ahead and stop there today. We can do more with this, and we will do more with this. We will be given sometimes grams of gases. We'll have to actually calculate our own mole ratio, but we'll do those practice problems tomorrow. That's your only homework for tonight, other than finishing the questions 1 through 5 on the worksheet you got today.